So today we will be discussing areas to discuss properties of conjugacy classes of alternating groups. I have kept my talk very basic, so if you have any doubt, please feel free to stop and ask me. So first I'll start explaining this term. So what do I mean by conjugacy class and what is the meaning of alternating group? Okay. So let G be a group. Then two elements G and H in G are said to be conjugate if there exists some X belongs to G such that this happens. Okay, and this is an equivalence relation on G, and the equivalence classes are called conjugacy classes. Okay, so equivalence classes are called. Okay, so now I define what is alternating group. I will be writing it with AN. To explain AN, first I will tell you what is SN. SN is symmetry group of degree N. So let's take S, this set containing n elements. To be specific, we are taking those n elements to be 1, 2, 3 to n. Then Sn is collection of bijective maps from X to X. And this selection forms a group under mutual composition of functions. And we know the size of Sn is n factorial. Okay. The alternating group An is a degree 2 index 2 subgroup. An is an index 2, so it's a normal subgroup, index 2 subgroup of Sn. What type of elements An contains? Let me explain. So, for example, so here if I take X to be 1, 2, 3, 4, then I have bijective map. So, for example, this is the bijective map from X to X. So this map I can write for shorthand, it is written this way. So 1 is going to 2, 2 is going to 1, 3 is going to 4, 4 is going to 3. And another example I'm going to take. So here, this will be written this way. So 1 is going to 2, 2 is going to 3, 3 is going to 4, 4 is going to 1. One more example I'm going to take. So this is basically 1, 2, 3, 4. 1 is going to 2, 2 is going to 3, 3 is going to 1. So usually we don't write these 4. So whatever element is missing, that means that element is fixed.
Use the mic, maybe.
Okay.
Okay.
No, okay. Sorry. I was told, but I forgot.
You want me?
Okay. So for shorthand, whatever elements are missing, we don't have fixed elements. So these parts are called cycles. So every element of Sn can be written as product of cycles, and further cycles can be written as product of two cycles. By two cycle, I mean this is a two cycle. Okay. So for example, I can write 1, 2, 3, 4 as a product of two cycles, 1, 4, 1, 3, 1, 2. And similarly, if I cycle contain an element, it can be written as product of two cycles this way. So every cycle can be written as product of two cycles. This way, any element of Sn can be written as product of two cycles. Okay. So now, for any element in Sn, there are two possibilities. The first one is that sigma is product of even number of two cycles. In this case, this is called even permutation. And others, as you can guess, those are odd permutations where that element can be written as product of odd number of two cycles. If you take collection of all even permutations that form a subgroup of Sn, that subgroup is called alternating. Okay, this is a subgroup of Sn containing even permutations. Okay, so with this, I completed defining the two terms in my title, conjugacy classes and alternating groups. Is this fine? So next, why we are trying to study conjugacy class properties and alternating group, I'm going to answer that question. So first of all, why did we choose alternating group? So one thing is that for n greater than equal to 5, alternating group is a simple group, and for group theories, simple groups are important because simple groups are building blocks of groups, just like the prime numbers are building blocks of natural numbers. Okay, in classification of finite simple group was the biggest achievement in group theory of the last century. So that's why AN is an important group. It is easy to understand finite simple group. So that's why we are interested in studying this alternating group. Second, why we are studying properties of the conjugacy classes. There can be many answers to this question, but my interest comes through because of this from representation theory side. So here, let me first define what is the meaning of representation. Let G be a group. Then any group homomorphism from G to GLNF is called representation of G. Then if you study representation theory, then important representations are irreducible representations. So what do I mean by irreducible representation? The representation which does not contain any sub-representation is called irreducible representation, and every representation can be written as the sum of irreducible representation. So if you know irreducible representations for some group, all irreducible representations for some group, in some sense you understand all the representations of that group. Okay, so what is happening that the total number of conjugacy classes of G is same as total number of irreducible representations of G. Now, here is one set containing conjugacy classes and here is another set containing irreducible representation. So it is known that the number of conjugacy classes is same as number of irreducible representation. But except for Sn, there is no bijective map known, some standard bijective map known from this side to this side. Okay, so people try to understand that how this correspondence is works between conjugacy classes and irreducible representations of the group. To understand this correspondence, they try to study properties of conjugacy classes as well as properties of irreducible classes, and then they try to relate them. That's why studying properties of conjugacy classes are important. There can be other answers to that question also, but my interest comes from this side. Okay, so now I'll tell you that what type of properties people study in conjugacy classes. So first is real conjugacy classes. A conjugacy class is said to be real if conjugacy class say C is said to be real if G belongs to C implies G inverse also belongs to C. If an element is conjugate to its inverse, then its conjugacy class is called real conjugacy class. The element is called real element and its conjugacy class is called real conjugacy class. Okay. And here if you see, this representation is mapped from G to GLMF. So image is basically a matrix. So what can I relate here? I can define character of representation, character associated with the representation. So how it is defined? Suppose phi is representation from G to GLMF. Then phi G belongs to GLMF. Then character is a map phi from G to GLMF, and phi is basically trace of this function. Okay, fine. And so what is happening that for real conjugacy classes,
You are considering with so phi is a matrix and then the addition of the numbers. This is not equivalence, right?
oh no, sorry, thank you. This is the entry. Okay. So what is the result known for long time is number of real conjugacy classes is same as number of real irreducible representations. What do I mean by real irreducible representation? So a representation is called real representation if its associate character is real value. So representation may be defined for complex field, but it may happen that this is mapped from G to R. If this is happening, then this map is this representation is called real representation, and this is how this property of conjugacy class is related to the property of representations. And one step down, if we go, then I will define rational conjugacy class. Let G be a group. An element G belongs to G is called rational if G is conjugate to Gn for all n such that GCD of n and order of G is known. Okay. So if a class is rational conjugacy class, if the conjugacy class is rational, okay, I have defined rational element. So if G is rational element, then it's easy to check. Then all the elements conjugate to G are also rational. Then its conjugacy class is called rational conjugacy class. Okay. And now this is the result by Navarro and T. I forgot the year. It is in transition of A and S. They have proved that a group has two rational conjugacy classes if and only if it has two rational value characters. After that, a student of Navarro, Dan Bosey, generalized this result to that if a group has three rational conjugacy classes, then it has three rational value characters. As far as I know, the other side is still open, but this is not true in general. There are groups where number of rational conjugacy classes does not match with rational number of rational valued characters. Okay, so after four, in the same paper, Rosie has given some example. That example is computed using computer algebra software GAP, where they have found a group which is having four rational conjugacy classes but six rational value characters. So this can't be generalized further. So I want to now discuss rational conjugacy classes for A. Is this fine till here? Okay. So shall I erase?
So here, whatever you said is applicable to a finite group, right? So that doesn't apply to,
Yes, yes.
so you're restricted to finite groups.
Yeah. The people study the conjugacy classes for infinite groups also, and all these
Yeah,
terms are
that's
valid there also.
No, but the number of.
Number does,
Yeah.
but it can happen even for infinite group that some numbers turns out to be finite, at least in case of G classes, not here. Okay, I'll go to Z classes. Okay, so next we want to discuss rational conjugacy classes for alternating group. So for alternating group in my paper with Sushil Bhunia and Anupam Singh, we have proved that the number of rational conjugacy classes is same as number of rational valued characters that is happening in alternating groups. But from after this, due to time constraint, I may not be going towards the representation theory side. I will mainly stick the conjugacy classes side of alternating group. Now to understand any type of properties of conjugacy classes of AN, first we need to understand the conjugacy classes of AN first. So we'll discuss the conjugacy classes of AN. So for that, I first discuss the conjugacy classes of SS. And conjugacy classes of in SN are in one-to-one correspondence with partitions of N. Now, what do I mean by partition of N? So N here is a natural number. So lambda is called, say lambda is a sequence, lambda 1, lambda 2, lambda r. This is called partition of N if N is equal to lambda 1 plus lambda 2. Now, just for convenience, sometimes we take either it is increasing sequence or sometimes take it either it is a decreasing sequence. So all these are positive numbers. These are the partitions of N. So for example, if we are N is equal to 3, Then we have three partitions. These are all partitions of 3. If n is equal to 4, then I have 5 partitions. These are all partitions of 4. Now these partitions are in 1-1 correspondence with conjugacy classes of Sn. So in S3, 1 plus 1, this always corresponds to identity element. 1 is going to 1, 2 is going to 2, 3 is going to 3. This corresponds to 2 cycles, which corresponds to 3 cycles. There are these 3 conjugacy classes. If two elements in Sn have same class type, they are conjugate to each other. Okay, in conjugacy classes in S4, this is 1, this is 1, 2, this is product of 2 cycles, this is 1, 2, 3, and this is 1, 2, 3, 4. Okay. Now, An is a normal subgroup of Sn. So let sigma belongs to An, that is sigma is an even permutation. Let C be conjugacy class of sigma in Sn. Then there are 2 possibilities, just for shorthand, I think it has C. Okay. So there are 2 possibilities. One is that this remains a conjugacy class in An as well. Okay. So what I'm saying that the first possibility is that the conjugacy class of sigma in Sn is same as conjugacy class of sigma in An. Okay. The second possibility is that this conjugacy class in An is splitting into 2 conjugacy classes in An. Okay. So when this happens, so this happens basically when centralizer of sigma in Sn is same as centralizer of sigma in An. If centralizers are not same, now I am finding another term. So shall I define what is centralizer? Shall I define?
No.
No, it's okay. Okay, so if centralizers are not same, then conjugacy class will remain same. Okay. So, and in terms of partitions, what is happening that this situation will happen. So now you know that every element of Sn corresponds to a partition. Okay. So this will happen if partition corresponding to sigma has odd and distinct forms. Okay. So here, this is if partition has some even part or partition has some repeated part. In that case, conjugacy class won't split. So for example, if you are looking here, so this is anyway containing just one element. This does not belong to An. This is the odd cycle. This belongs to An. The partition here is 3. It has only one part and that part is odd. So this conjugacy class will split into 2 conjugacy classes in A3.
I'm just observing something, and that's why I'm just asking. I'm finding out a pattern. It's like 1 plus 1 plus 1, then it's 1. When there is a 2, so there will be this 1.
This is that
And 3. So
that is how they are in. Okay. Okay. So here when I'm saying this is 1 plus 1 plus 2. So here this is 2 cycles. Here this is 3 is fixed, 4 is fixed. Okay. So here this is 1, 2, 3, 4. Here 1, 2, 3 cycle and 4 is fixed. Here this is a 4. That is how this correspondence is.
Basically, like if you have 1, 2, 3, that's a representative. So anything with the same title structure,
They
you
will
can
go to
plug
the
it. You
same
can
function.
multiply it, make 2, 3, 4, and other things.
Okay. So here this is identity class. So this does not belong to An. This belongs to An. But here if you see, here is also an even part and parts are repeated also. So this conjugacy class remains a conjugacy class in theory, it won't split. And this belongs to, again, This belongs to AN, and here corresponding partition is 1, 3. So this will split into two conjugacy classes. And this is the odd circle, odd permutation. So this does not belong to A. Okay. And on this basis that whether the conjugacy class will split or not split, for my work, I have divided the conjugacy classes of AN in two types. So one is called split conjugacy classes. Okay. And other one is non-split conjugacy. Fine. Okay. So next we want to find rational conjugacy classes of, I think I said, rational conjugacy classes of AN. So first of all, Sn is very nice way. All conjugacy classes of Sn are rational. Okay. This result helps me in saying that non-split conjugacy classes of AN are also rational. Okay. So if X belongs to AN and conjugacy class of AN of X in AN is same as conjugacy class of X in Sn, then X is a rational element. So this conjugacy class is a rational class. So proof is pretty easy. So let me just write those couple of lines of proof of this step. So what I need to show, what is the definition of rational conjugacy class and recall it. So a class is called rational conjugacy class if X is conjugate to X to the power M for all M such that GCD of M and order of X is 1. Okay. Now, because all conjugacy classes in Sn are rational, fine. So in Sn, X is conjugate to X to the power M for GCD of for all such M. So what is happening that this is in Sn for all M such that GCD of M and order of X is 1. So what is happening? So what do I mean by in N? So this G element is coming from Sn. Okay. If this G belongs to, there are two possibilities. If this G is already in AN, then I'm done. Nothing to do. If G is not in AN, okay. If this is not in AN, then see what is happening here. In this case, centralizer in Sn is not same as centralizer in AN. That means there is some odd permutation in Sn which is in centralizer of Cp. Okay, in this class. So this means there exists, say we will call Y, an odd permutation such that Y belongs to centralizer of X in Sn. So what do we have? Y, X, Y inverse is same as X. Now you combine this G and Y and we will get an even permutation which is basically giving that X and XM are conjugate in AN as well. Okay, just take the product of G and Y that will give us the that X is conjugate to XM in AN as well. So here things were pretty easy. So for other part, Now we are in situation. So X belongs to A and conjugacy class of X in essence splits into two conjugacy classes. Then we want to determine whether these two conjugacy classes are rational or not. Okay, and this result was proved by Brisson in 1989. Paper was alternating groups. And with conjecture about rational and correct. Okay. So in this paper, what they have shown that either both C1 and C2 are rational or both are not rational. And when they are rational, that again depends on the partition. So you remember that if the conjugacy of class of X splits into two conjugacy classes, then let lambda be partition corresponding to X. Then lambda will be of odd distinct parts because class is splitting into two parts. So each lambda I is odd and lambda I is not same as lambda j for I is not same as. So this is the partition corresponding to that. So Brisson have proved that both C1 and C2 will be rational conjugacy classes. If product of parts of this partition is a perfect fit. I'm not going to discuss proof of this part because that is quite involved. So this is the result. And first time this happens when n is equal to 9. Okay, in n is equal to 9, we take this partition of 9 partition of 9. Then here are odd distinct parts and it is a perfect sphere also. So because odd distinct partition will break into two parts and both of these conjugacy classes will be rational. Then the next thing, this will happen when n is equal to 10 partition, you can take 9 plus 1. Odd distinct part, class will split into two parts and again the product is 9, so it's a perfect sphere. Then it is happening in 23, 5, 3, 20. I should write this way. Okay, so here again odd distinct parts and class will split into two parts and conjugacy classes. Similarly, there are then after that there are so many examples, but if you are looking in very small an, then there is no such example. Of rational split rational conjugacy classes happens first time in n is equal to 9. Okay, so I stop here for a minute because one part is over. Any question?
So it's not an economic statement, right? That result, the last.
Yes, this is it.
Oh.
Both. So thank you. Thanks for pointing out. Anything? Any question?
I just want to know that here you are considering the product of lambda I, that's your perfect square. Have you ever tried with something which is not perfect square, but there it has a perfect square part?
It is.
It's like, n square view, that kind of.
You're saying this way?
Yeah, it's like, have you tried this kind of thing?
No, I didn't get your question. So what are you asking?
And so I'm asking that, so here you have taken this product to be a perfect square.
Yeah.
So it's like n square kind of thing.
Hmm.
So, I mean, have you encountered?
So it will not turn out to be n square. So suppose we are taking n is equal to 23, then you can take this partition 3, 5, 15. So it's not coming out to be n square. It has to be a perfect square. It can be any other.
That is,
It's not
this
related to n.
statement is fine.
Yeah.
But my question is that if I change the condition to something else, whether there is any result related to that or not. So
So
for
if-
example, if I'm considering this as the, let's say, perfect square into some other thing.
Into some other thing.
Yeah.
That class will not be a rational conjugacy class.
Yeah,
There could be some other.
Something, so have
No,
that,
I'm going to-
encountered anywhere as of now?
No. Okay, so is it okay till here? Fine. So next, I'm going to move towards G classes in AN. So in AN, this is happening that the number of, after doing this, if we count number of rational conjugacy classes, that turns out to be same as number of rational valued characters. Okay, that we have proved in our paper. So next I'm going to discuss G classes of alternating group. So before discussing G classes in AN, I can discuss G classes in SN. Okay, so and here also this results were proved by in same paper by William and Anupam Singh. Okay. And the term G classes were defined by Gangotadhyay and Kulkarni in 2008, I guess. So initially this term was defined. Yes. Again, not defined G classes yet in 2009. So initially, these G classes were defined to understand dynamics of hyperbolic spaces. But later on, people find out that this is an interesting notion, interesting invariant even in finite groups also, and people started to study it in terms of in finite groups. There are many papers related to G classes in finite groups as well. So what is definition of G class? So first, let's G be a group. Two elements G and H in G are said to be G conjugate. If centralizer of G and centralizer of H are conjugate subgroups in G. Again, this defines an equivalence relation on G. And the equivalence classes are called G classes. The first result I'm going to say that if two elements are conjugate, then they are also G conjugate. But other way around is not true. So basically in G conjugate, G classes, we are clubbing conjugacy classes in single one. And in this term was, as a G classes was defined by Gangopadhyay and Kulkarni, but it was studied even at the time of Green also. There they were calling it types. So if you see representation theory of GLNF, then the conjugacy classes of GLNF, whenever we discuss, they are divided into four parts depending on the type of conjugacy classes, if the scalar matrices, then diagonalizable matrices, non-diagonalizable matrices. Basically, those four types are Z classes. And similarly, then even when we study representation theory of GLNF also, they can their representation can also be divided into these four types, and those four types are nothing but Z classes. So GLNF is infinite group, but here the number of conjugacy classes turns out to be finite. If I'm not wrong, because I don't study infinite groups much, but as far as I know, there are some infinite groups known where Z number of G classes are finite. Okay, so I'll just explain this result quickly. If two elements are conjugate, then they are also Z conjugates. So let X and Y belongs to G and X is conjugate to Y. This means there exists G belongs to G such that X is equal to G by G inverse. So next, let this is centralizer of X. This is centralizer of Y. Then I want to show that their centralizers are also conjugate. So let K belongs to centralizers of X. So this means K inverse is equal to X. So next my claim is this is if I put everything correctly. G inverse belongs to. Maybe I need to change this inverses and see that. So if I do this way, this is one. So from here, this is equal to X. So now because K is in centralizer of X, so this is X. So this is now. Oh. Correct. This is right? Or I'm doing something. So basically, this thing will work. So this is give me that with the same. Okay. So conjugacy will imply G conjugacy. Okay. So what this for a minute. So next we want to discuss conjugacy, Z conjugacy in alternating group and their relation with the rational conjugacy classes of alternating groups. So before that, to give you a feel, because we have some time, I think I don't know. Okay. Hey, let me discuss that how do we do it. So in this paper, we have computed Z classes for both Sn and An. So let's see how it is done. So using this result that if two elements are conjugate, then they have G conjugate also. So we don't need to worry about all the elements which are conjugates. So first thing we compute conjugacy classes because that is always known. Okay, so to compute G classes, so first we compute conjugacy classes of G. Then we choose representative from each conjugacy classes. suitable representative which is easy to work with. Okay. So next we compute centralizer of each representative computed in step 1. Third is the recheck whether any two centralizers computed in step 2 are conjugate or not. The first two steps are easy or known for most of the groups we are working with. So these two steps are fine. This is the hard step to check whether all those are conjugate subgroups or not. And it may happen that even when the conjugacy is something more than isomorphism. Okay, so means conjugate, if two subgroups are conjugate, that means they are isomorphic, but other way around is not true. The two subgroups may be isomorphic to each other, but they may not be conjugate. So conjugate, this the third part is very hard to check usually. So in our paper, to bypass to check whether two subgroups are conjugate or not, we take the help of group action. Okay, and Sn has the natural action on set X containing m elements. So Xn acts on this set naturally. So what is this group action in case of Sn? Sn acts on X. So basically by group action I mean I need a map. So do you know what is group action? Shall I define it? No, okay. So I need this type of map. So basically in case of Sn, I will just evaluate that map on that one. So this is the group action. And this group action can be restricted to all subgroups of Sn. So basically it can be restricted to An, it can be restricted to centralizers, and it can be restricted to center of centralizers also. So after computing these two steps, so basically in case of Sn, conjugacy classes that we know, centralizer also we know. So after this what we do, we compute center of centralizer. Okay. Then we make it act on X because it is a subgroup of Sn. So the same group action is restricted to the center of centralizer, and this step helps us in determining G classes of Sn. And in case of Sn, what is happening that so in case of S3 and S4 also, the conjugacy classes is same as G classes. There is no difference. So first time in S5, this is happening that two different conjugacy classes become a same G class. That is happening in 1, 2, 3 and 1, 2, 3, 4, 5. So these are not conjugate in S5, but they form same G class. And that is the only case when this happens in S5. So basically always this happens that if here two elements are fixed and in other those two elements are forming a single group. Only in that case they form in same G class in case of Sn. Okay, but the results are not this neat in case of En. First of all, the centralizers are also pretty picky. So in case of En, so let me erase this part. We have divided conjugacy classes into two parts. One is split conjugacy classes. Other are non-split conjugacy classes. So for non-split conjugacy classes. Here we are using the same technique as we have used for AN. So we are computing their centralizers in AN. Okay, and then we'll find center of centralizers in AN, then make it act on. So here what we are doing in case of non-split, we are computing its centralizer in AN, then center of centralizer in AN, and make it act on X that determines G classes for AN for us using the same technique. But the result is not as neat as SL. But the problem comes in split conjugacy classes. So what is happening here is a conjugacy class in SL. It got split into two conjugacy classes. Now here two possibilities are there. So number one is that these both can be in same G class, or they can form different Z class. Okay. Now when does this happen? So in terms of partition theory, I will tell you. So let so because this conjugacy class is splitting, so let lambda is equal to lambda 1, lambda 2, lambda r be a partition corresponding to sigma. Okay, so then all these parts will be ordered distinct because the conjugacy class is splitting. This splits only in this case. So this case will happen. Oh, okay, let me remember which one is happening. Okay, so distinct conjugacy classes will happen. This will happen if and only if all parts lambda I are perfect squares. And this will happen if some part is not a perfect square. Okay. So here, if each part is a perfect square, only then they form different Z classes. If some part is not perfect square, then they form same G class. Okay. And the other thing can also happen that this. So here, first I had single conjugacy classes in SL, they split into two conjugacy classes in AN, but they are becoming same G class. But it can also happen that two non-split, two split conjugacy classes can also become a Z classes with another non-split conjugacy class. So how to see that? Two split conjugacy classes plus one non-split conjugacy classes sometimes may combine to form same G class. So here basically three conjugacy classes are making same G class. Let me tell you the smallest number where it is happening. So this happens for n is equal to 20. So here these partitions okay, we are writing this way. These are two split conjugacy classes, and this non-split conjugacy classes, all three form same G class. So because of so after this, the count is somewhat combinatorial, and after doing all this calculation, we did this count. So let me write the final result, then I will stop. number of G classes in AN is equal to conjugacy classes in AN minus, I'll tell you what these terms are. Okay, this is the number we have computed. So the conjugacy classes in AN, this is number of conjugacy classes in AN. This is equal to, I think, partitions of N plus 3 times Qn by Q. Right? Yeah. So now here Pn denotes number of partitions of N. Okay. And Qn is number of partitions of N with odd and distinct parts. So you can see that this Qn over here is taking care of splitting of conjugacy classes, and this Q tilde N is number of partitions of N with odd distinct parts. Where 1 and 2 are not appearing as parts. This is taking care of merging this type of partitions here. So 1 and 2 are not coming as a part. I think 1, 2, and 3 should come. Does not appear as a part. And this En is number of partitions of N with odd, distinct, and perfect pure parts. So here earlier we were subtracting, and we have added this to take care of that. Here this forms a separate Z class. Okay, so I stop here. Thank you. Any questions?
Are there any other refinements in partitions that we see which come up in the accounting of these conjugacy levels?
Yeah, I know only this much about these conjugate classes. In Z classes, these are requirements are there. But if you want to study different type of properties, then you can use different type.
There are very special sort of congruence results in partitions. But if you have something like numbers of the form 5 equals 4, and every part will be divisible by 5 and so on.
Okay.
Do these results help somehow in counting these conjugacy levels?
So usually here what we are doing, we are finding the centralizer. So in centralizer, whether centralizer will contain some odd partition or not, that depends on whether those parts are perfect squares or not. So whether they are congruent to something, that is not helping in this case, at least.
Yeah, thanks. Very interesting results.
Thank you.
What actually you were saying, and then there can be some promising research direction where so there are many number theoretic identities involving partitions and
Yes,
there are the
partition
powers of all. Yeah, so because these numbers are appearing here, so there
Yes.
must be some connection.
Some connections.
And you create some generating series, right?
Yeah.
Then, for example, you can create some generating series with these,
These.
right? Like you just write like sigma qn,
Hmm.
an qn. I mean, the coefficient an actually is your CLAN,
Hmm.
and then study those generating functions.
Okay.
And then that would probably lead to something.
Yeah. Partition theory is itself very vast area.
Yeah.
It's an area of research. So I don't know much about the partition theory.
Yes, okay, it's very interesting.
Thank you.
Thanks.
Yes.
So is there any other class of simple groups you can expect such result?
Yeah, we are now trying further expecting so this correspondence for other finite simple groups. We are exploring that. So basically, I'm trying to do that for PSL. But
PSL.
yeah, so here the things are not that easy, like in AN. Because in case of AN and SN, due to this partition theory help me understand conjugacy classes very well, but that is not the case for other simple groups.
So suppose you know the conjugacy classes, then you're taking the group action approach. Can you apply it in other cases? In case you know the conjugacy.
Yes, basically I told you those the 3 steps we need to
Yeah.
do. The usually conjugacy classes is known for finite simple groups. Centralisers are also known. Maybe difficult to understand, but mostly known. The third thing is the difficult. Then two centralisers are conjugate or not. That is the part need to understand. But yes, and people, Navarro and T studies this rational conjugacy classes and their relation with characters frequently, but they are mostly interested in the finite group setup. They are not going to the particular examples.